CAD development started in the mid-70s and it replaced manual drafting. In engineering, it is the most widely used form of modeling. Advantages are numerous. Just to name a few: an automated generation of the bill of materials, interference checking, engineering calculations, and it also allows rotations around 3 axes, allowing to view an object from any angle, even from the inside. These unique features result in lower product development costs and a shortened design cycle. Related technologies and spin-offs are CAE, Computer-Aided Engineering, FEA, Finite Element Analysis, and CAM, Computer-Aided Manufacturing, and there are even more. As I said, there are several ways to accomplish 3D printing, but they all have the following in common. Parts are constructed layer by layer from powdered material. It is an iterative process, that is to say, material is added bit by bit to obtain the final product. In contrast to more conventional manufacturing techniques like milling, material is added to obtain the final product instead of subtracting it from billets, castings, etc. And an energy source is needed to fuse the particles together. The object on the left is an A380 part showing complex shapes that can be manufactured. However, I would like to emphasize that far more complex parts are also possible. Please note the picture on the right. I took this last June at the Paris Air Show. It shows 2 equivalent parts having the same functionality. The left one is 3D printed, while the right one is machined. I think the weight saving by printing is obvious. There are many different ways of processes to accomplish 3D printing. The ones most relevant for aerospace and defense applications are listed here and discussed briefly in the next slides. SLM, SLS, and DMLS are related technologies. SLM stands for selective laser melting. SLS is selective laser sintering. DMLS is direct metal laser sintering, while EBM is electron beam melting. SLM, SLS, and DMLS are quite similar processes. The main difference is that SLM achieves melting, while SLS and DMLS achieve sintering. In all cases, a laser is used as the heat source. DMLS is a further development of SLS using a more powerful laser. This results in higher build rates. A 3D CAD file is used to model the parts to be produced. The technologies can be used with titanium and various other metals. The process is time-consuming, although this applies less to DMLS. Therefore, it is primarily suited for small series. These technologies are pioneered in the aerospace industry and also in medical orthopedics. EBM is electron beam melting. The beam is computer controlled, receiving its data from a 3D CAD model. As the name implies, the heat source here is an electron beam. In contrast to SLS, full melting is achieved. The part is constructed under vacuum, which makes it a suitable technology for titanium because this has a high affinity for oxygen. The process typically uses pre-alloyed material. The energy density is higher than with SLS. Consequently, the build rate is higher. High quality, dense parts without porosity can be produced. This allows the post-process sintering process to be omitted. Aerospace, we cannot afford to take risks, as safety is of paramount importance. Consequently, when implementing new technologies, a conservative approach is needed. When applied to the technologies discussed here, this means we tend to go from non-load carrying elements to elements or structures that are statically loaded, and from there to dynamically loaded structures that may be fatigue critical. An example of a non-load carrying element is shown here. General Electric has developed a 3D fuel injection nozzle for application in its LEAP engine. 19 of the nozzles are used in the combustion system of the engine. The part is already flying or will fly very soon. The benefits include about 25% weight reduction from the predecessor part, much simpler design, there are new design features, and this results in an estimated in a five-fold improvement in durability. In conclusion, we could summarize the current state of affairs regarding the technology as follows. On the plus side, we have the following: a very high material conversion rate, highly complex geometries can be produced, reduced overall complexity due to smaller number of parts and less associated joints. It allows manufacturing of geometries otherwise impossible to obtain. There's no bespoke tooling necessary. It can be considered a green technology, and it's suitable to manufacture near net shape, high value, medium-sized parts. The drawbacks, quality or consistency thereof is still an issue. Mechanical properties of the end product are still insufficiently known. There's a lack of available data, although this is expected to improve. Certification and qualification issues. The production rate is still a problem, although progress is being made here as well. And the technology readiness level is still quite low. Okay, without the last line. This is what I wish to share with you this morning. In case you appreciate more information, please feel invited to contact me. And thanks you again for giving me this opportunity.